All right, so can you guys see my screen now?
Yes, sir.
All right, so for the module 3, we'll talk about linear applications of op-amps. So as you guys may all know, there are two types of op-amps applications. So we have the linear, okay, and then the non-linear applications, okay. So for the linear applications, we have 7, and then for the non-linear, we have 5. So as you can see, we have already finished number 1 and then number 2, okay, which is the inverting and then the non-inverting amplifier. Okay, so we are now in number 3, which is the unity gain buffer, or sometimes you call this one voltage follower. Okay, so we will discuss them one by one, but for now we will talk about unity gain buffer or voltage follower for now. So just ignore the others to avoid confusion. So just focus on the number 3 for now. Okay. But before that, so let's just recall, okay, what is the open loop and then the closed loop configuration, okay, what are they about? So for the open loop, so again, this one indicates that there is no connection exists between input and output terminals at of any type of circuit, okay, or any type of amplifier. So this is the open loop. So as you can see, our V out is as it is. Okay, it will not give a feedback to our input. Okay, so it doesn't have a connection or a feedback resistor. Wherein output signal will not give any feedback to our input signal. Wherein as a result, this will always give you a high gain. Okay, it's like 120 times or 1,000 times higher. Okay, like your 1 volt will become 1,000 volts. But then again, this one is unusable, okay, in real world, because having a too much high loads or too much high gain is uncontrollable. Okay, it's not stable. Okay, so that is why we have the closed loop configuration. Okay. Anyway, before the closed loop, we have here the features of open loop. So again, yeah, it has no feedback, very high voltage gain, cannot be used as a linear amplifier, okay, because it has a super high gain voltage. And then this one is only used in comparators and waveforms distortions take place. So as you can see, waveform distortion takes place because having too high or too much gain can give you too much noise at the same time. Okay, so it has a consequence also, not only giving you a pros wherein, yeah, you're getting a high gain, but at the same time you're also getting a high noise, okay, or noise level on your waveform. Okay, so yeah, that's it for the open loop. And then for the closed loop, it has a feedback. Okay, so it's completely the opposite of the open loop, where it has a feedback resistor, as you can see right here. We have the RF from the output to the input in the circuit. So it is a part of output is returned or fed back to the input. So instead of having all the outputs in here on the V out, okay, some of them will go to our inputs, okay, or to our uh, inverting input. Okay, so this is our V in, and then this is our inverting inputs. So it's like dividing the total uh, gain of this certain amplifier. Okay, so the benefits of having a closed loop is, of course, it's like just completely the opposite of this one. Okay, you will get uh, oops, low voltage gain, but in return, you'll get a stable and more controllable voltage. Okay? So this can be used, of course, if you have feedback. This can now be used as part of the linear applications, okay, or linear op-amps. Okay, and then at the same time, it will not give you, or it's not susceptible to waveform distortion, because only gives you a smaller, so yeah, not really smaller, so it's still high, okay, but it is now controllable and lesser distortion of waveform. Okay, and one more thing, we have here the types of feedback. Okay, so Maybe you guys already know this one. But we have the positive feedback or the regenerative feedback, and then we have the negative feedback or the degenerative feedback. So this one is actually like saying that if your input is positive, then you must also get a positive output, right? If the case is like that, then we call that one positive feedback, or it is in the same phase. Okay, we are in line with each other. Okay, positive, positive. However, if you say you have a positive input and then you have a negative output, we call that one negative feedback or degenerative feedback, wherein it's 180 degrees out of phase. Meaning, it has the complete opposite of your original waveform. So originally, let's say you have a positive waveform, but your output will give you a negative waveform. Okay. So those are just the types of feedback that you will get out of an amplifier. All right, so this is just a recall. Let's now move on with our main goal for this module, which is the unity gain buffer, okay, or sometimes call this one voltage follower. All right, so is there anyone here who has an idea what is voltage follower? Where do we use such circuit or amplifier? Anyone? Hello? You guys still there? Ako iniwan na ako. Wala nang tao.
Dito pa kami, sir.
Hindi pa ba kayo? Okay. So, sa main chat, nawala yung chat. No idea, sir. So, no one here has an idea about voltage follower. Walang idea, sir. Okay. So, supposedly, I will not give this one as your laboratory since this one is quite useless, actually. Okay. But not in terms of I can disregard it and then not learn what is voltage follower about. Okay, so as you guys may all know, going back here, an amplifier, just from the word itself or just from the name itself, it amplifies the signal, right? So having a low voltage or low input and then having a high output or high gain. Okay, but in a unity gain buffer or voltage follower, okay, it doesn't do anything with your uh, inputs or with your signals. So whatever is your input, it will give you the same output. So it's 1:1. Okay? It will not do anything. So that is why in voltage follower, V out is always equal with your V in. Okay. And then this one is gain with feedback. Yes, this has a feedback or a closed gain of this circuit is 1. Okay, so you will know later on why this one is 1. And it is a special case of non-inverting op-amp. Okay, so take note, special case non-inverting op-amp. So this is really super special because it's under amplification or amplifiers, but it doesn't amplify your signal. Then, of course, this one is similar with non-inverting because your input is on the non-inverting side, and then it also has this feedback resistor. Okay? But then again, it's an special case. Okay, so therefore, in this circuit, the output signal is in phase with input signal. So how do we know, or how did we know that the output signal is in phase? That's because your input is in the non-inverting. So can you guys still remember? If your input is in inverting, you have a positive input, it will become a negative output. But for the non-inverting, whatever is the sign of your input, it will not change anything. Okay, so it will stay as it is. So yeah, it's in phase. Okay. So feedback resistance. RF is equal to 0. Okay? And then R1 is equal to infinite. Okay, that's the default value when it comes to having a voltage follower. Okay, so that is why if ever you're going to use a formula later on, which is it in here? Yeah, it's in there. Okay, you will get the same input or the same output. Okay? It's always like that the case. So V in is equal to V out. Anyway, here's the voltage follower circuit. So we have here the R1 and then the RF, and then of course this one should be grounded. And then we have here the voltage input, okay, which is connected with the non-inverting input. And then we have here the outputs. So as you guys may all know, this one is virtually short circuit. So what do we mean by virtually short circuit? So initially this one, positive and negative, it's like they are not connected with each other. But in reality, they have or they are connected, which is we call virtually grounded. Okay, because of course this one has a loop wherein this one is grounded, this one is also grounded, so they now have a connection in a way that they are virtually short circuit. Okay, so we have here the R1, okay, wherein it is always equal to infinite, and then your RF is always equal to 0. Okay, so since if you can still recall, since an amplifier always try to make the input on the non-inverting and then to the inverting, it always make the inputs equal with each other. Okay, so that's the minimum rules when it comes to amplifiers. So it always try to make this input equal with this input also. So if you're going to take along this one, uh, V2 is equal to V in, okay, which is your voltage input. And then going back to the rules on our amplifiers, since V2 is equal to V in, V2 must be also equal to your V1, which is the voltage input of your inverting. Okay? So that is why you could say that V1 is equal to V sub 2 is equal to V sub in. All right. And then that is why whatever is your input, we'll just go back here. And then if you're going to solve this one using this formula, you will get this result. V sub O is equal to V sub E. Okay, so here's the computation. So the output voltage follows the input voltage. That's the reason why we call this one voltage follower. So in other words, V out is equal to V in. So here's the formula. Okay, so this one is just a simple formula for getting the gain for an amplifier. So 1 plus RF divided by R1, wherein R1 is infinite and then RF is 0. So if you're going to do the math, okay, you will get this one. So 1 plus 0 divided by infinite is equals to 1 plus 0. Okay, so this one is actually just 0. So nothing's happened. Okay, thus having now only 1. Okay, so your gain is just 1. Okay, so as you can see, it didn't amplify your voltage input. So whatever is your voltage input, it's the same. It's just going to be multiplied by 1. Okay. So what else here? So since P out is equal to V in, voltage wall doesn't provide any implication, which is this one. So this is just another continuation or expansion of explanation. But just from here, you could already see that AF is equal to 1. Okay. So that is the reason why a voltage follower doesn't do anything. Okay, so as you can see, it's quite useless, right? Because why would you uh, input a voltage in here if it will not do anything with that voltage? So it's like just a wire, okay, that just passing through on that certain line. Anyway, we have here the reasons on why we're going to use such circuit. So reasons for using a voltage follower. So it has also an importance. So a voltage follower does not increase or decrease the amplitude of the input signal, and it does not filter out high frequency noise. Thus, you might be wondering why a circuit like this is so useful. Okay, so it says here this one is useful. It is true that a voltage follower that does not intentionally alter the amplitude or frequency characteristics of the input signal, but it does allow us to improve impedance regulation shifts. So, going back to the Ohm's law, as you guys may all know, when it comes to Ohm's law, uh, the more load or the more resistors that it will pass through, the more that your voltage or the more that your current will decrease, right? But in voltage follower, okay, it neglects, like it's like removing the noise level, or instead of having a voltage drop, okay, on each resistor or on each load, okay, it will not uh, lessen or decrease your voltage input. In fact, it will maintain it. So you can say that this voltage follower is a maintainer of our voltages. Okay. So whenever we are sending a voltage signal from one subcircuit to another, we have to consider the output impedance of the source subcircuit and the input impedance of the load subcircuit. Okay. Thus having a lower uh, voltage output. Okay. So the source's output impedance and the load's input impedance form a voltage divider. Okay. And consequently, voltage transfer depends on the ratio of input impedance to output a certain impedance. So this one is effective voltage transfer requires a source circuit with low input impedance and a load circuit with high input impedance. So meaning, to make it short, it neglects the voltage drop and then it still maintains the voltage input. Okay, so just by applying voltage divider, okay, so we can control, okay, so we can control the voltage output that we wanted. So for example, we have 5 volts. We want to control it to make it 3 volts, or we want to control it to make it 4 volts. So we can do it just by applying a voltage divider. Okay, so it's like actually the main use of a voltage follower. So it is always uh, intact with a voltage divider. So it's not just like a voltage follower circuit. It also has a voltage divider circuit in it. Okay, so take note on that one, because in that case you will be able to control the voltage output. But however, okay, since this one is just only maintaining the maximum, so whatever it can provide, let's say 5 volts, then it can only provide 5 volts also. It cannot provide uh, higher than that, like 6 volts, 7 or 8 or 9 or 10. Okay, so you can control it below, like 4 volts, 3 volts, 2 volts, and then 1 volt, but not higher than 5 volts. Okay. So here are the other reasons wherein with the use of voltage divider. So a voltage follower has low output impedance and extremely high input impedance. And this makes it a simple and effective solution to problematic impedance relationships. So if a high output impedance subcircuit must transfer a signal to a low impedance subcircuit, a voltage follower placed between these two subcircuits will ensure that the full voltage is delivered to the load. Okay, so one example of this one is this simple circuit. Okay, so it's a voltage follower wherein we have here a voltage divider. Okay, so it's a combination of those two circuits. Okay, so knowing that one, okay, I'll give this one to you as your laboratory number 10. Oops. This is number 10. Yeah, there you go. So this is your 10th laboratory. So I would like you guys to create a voltage follower wherein it will only give you an output of 50%. Okay. So design a voltage follower with a voltage divider on it. assuming that you have a 60 volts input voltage with a frequency of 60 hertz. So create a circuit wherein it will only output 50%. So I guess this one is super straightforward. So 50% of the original input voltage. So take a screenshot of your schematic and graph of the V in and V out. Okay. So I would like you guys to create a circuit wherein it will only output 50%, 80%, 20%, and then your reflection or conclusion on the circuits that you have accomplished. So from those circuits or problems that you have accomplished, what are your thoughts about voltage follower? So what are the benefits of it in our circuit industry? So why do we still use such amplifier or linear applications of amplifier? So give a scenario on this one. Okay, so we have 4 questions under voltage follower. So again, as I mentioned a while ago, it cannot amplify, but you can control the voltage output. So I'll let you guys read this one for 10 seconds. And then verify it one by one. And then you might have a question. So all of those are the same circuitry, just a different output. All right, so is your 10th laboratory clear so far? Or you're confused? No? Are you guys still there? Percentages. Okay, so what is your question about percentages, Mr. Pacific?
And I'm not understanding the role of that percentages. How are we implement percentages?
So, because you're the one who's going to create the circuit, right, Mr. Pacific?
Yes.
And then in creating that circuit, of course, you're going to have a voltage divider, as I mentioned on the uh, instruction. Okay, so voltage follower with a voltage divider on it. Okay, and then if you're going to take a look on the example in here, this simple circuit, we have here resistors. So
Mm.
those are the values, okay, or those ohms or resistance are the one that you're going to control or change from time to time to have an output of 50%, 80%, and then 20%. So what is the 50% of 60 volts? So I'm expecting 30 volts output. And what is the 80% of 60? Okay, so I should see 80% output on your circuit. And then what is the 20% of 60? Okay, so I should see 15 volts of output. Yeah, is it 15, 15, 30? I don't know. It's 12, not sure, but uh, 60 times 0.20, and you will get that output.
Okay.
Right. So this one is actually quite simple, since you guys already know have an idea what is a voltage divider. This one is like a bonus already. 10 A, 10 B, and then 10 C. So you might need some trials on how to come up with the 20% V outs. Any other uh, questions or clarifications? So is it okay now? Or would you guys like to take a look on your or take a look on this one more for 1 minute or for 2 more minutes? Well, anyway, so yeah, I think that uh, you're having a hard time in understanding this one because maybe this is your first time in uh, having a problem and then solving it by creating a certain circuit on the auto spice. Because before, of course, as a starter, as a beginner, I gave the schematic and then I gave the values of that schematic. And all you need to do is, do it, copy it, and then just run it, and then just uh, get the graph of the V out and then the V in, and then take a screenshot, and then that's it. But for this one, so you have to analyze this one a little bit more. Okay. So let's say that this one is a little bit more hard. Well, anyway, so we cannot stay here forever. So that's it for your 10th laboratory. If ever that you have a question or clarification in the future, as long as you're not asking on how to do it step by step, then I will help you. Okay. So sorry for that one. Anyway, so let's now proceed to the next one. So after the unity gain buffer or the voltage follower, so we have here the voltage to current converter. Okay. So what is this voltage to current converter? So as its name implies, it converts the voltage or the voltage source into a current source. Okay. So why do we do this? Because voltage signals in a parallel circuit may vary from one to the other due to resistive wire losses. So as you guys may all know, voltage always uh, has a voltage drop when it comes to passing a wire or passing a resistance, okay, or a resistor. Okay. But for current, okay, current sensing instruments typically have low impedance while voltage sensing instruments have high impedance. Wherein if we have a current source, okay, this one has a greater electrical noise immunity, meaning there's a lesser chance that the voltage or the current itself will not slowly degenerate. Unlike for the voltage source, so the longer the distance or the longer the wire, the more voltage that it will drop as it goes to its destination. But for the current, okay, it's stable. Okay, whatever is the current on this wire is the same with the current on the uh, end of that wire. So that's the benefit of having a voltage to current converter. Okay, so here's the solution. So we have to convert this voltage into a current source. So that is why we have this V to I conversion. Wherein in this V to I conversion, we have this circuit. Okay, so let's say this one is a TV or a display or any device. Okay, so to avoid voltage drop or voltage loss, okay, so we have to convert this voltage into a current. So uh, one benefit of having a voltage to current converter here is the It does not matter what the resistant value our load is or how much wire resistance is present in that large load. So long as the op-amp has a high enough power supply voltage to output the voltage necessary to get 20 milliamps flowing through the R load. So this 20 milliamps is only specifically on this circuit. So as you can see, we have here, let's say, a 5 volts or ranging from 1 to 5 volts input. And then if we have 1 volt, of course, you will get 4 milliamps. And then if we have 5 volts, then we will get 20 milliamps. So how did we get this one? Just by using this formula, which is I is equal to V divided by R. So V is, let's say, 5 volts. And then your R load here is, or your R here is 250. So 5 divided by 250, you will get 20 milliamps. Okay. If you have an input of 1 volt, then you will get 4 milliamps. Okay. And so on and so forth. Okay. Depending on the values of your resistors. So it doesn't matter if we have here an R load or a resistance of 1000, 1500, 2000, as long as we have enough high power supply.